Okay, good afternoon. So we're going to continue our discussion of the Kondo lattice model and talk about its phases. Then in the remainder of the course, my plan is to talk about just disordered metals in general a little bit. Then about random matrix theory a little bit of free electrons. Then the SYK model, and then about Fermi surfaces coupled to gauge fields. And that should be the end of the course. And also I'll be, I think, most likely giving one more problem set. It won't be a long problem set because I realize you're now busy with preparing your course presentation, or at least should be, start reading the article. At least you've chosen the article and are reading it. If you have questions or need help with understanding what's going on, I'm happy to help, and I'm sure Darshan and Ryan. Okay, so there will be one shortest problem set on basically the Kondo physics, and we'll probably end there. And also Darshan has sent out a sign-up sheet for your presentation, so please pick a slot. If none of those slots work, I'm willing to open up slots later, but let me know if you find that nothing's working for you. So all the slots are, I think, reading period essentially. So right after classes end on the last week of April. Okay, any questions or comments? All right, so we're continuing our discussion of this model called the Kondo lattice model. It applies to many interesting compounds, sometimes called heavy fermion compounds. They typically have a heavy fermion metal like cerium or uranium or something, where the electrons, the active electrons or the unpaired electrons are heavily localized, and that's what we represent by the spins. And then you have a conduction electron of mobile electrons that are typically from SRP bands or D bands of lighter elements. But also these days, of course, the Kondo lattice also applies, to other systems. People putting magnetic atoms by hand on the top of a surface of a metal, and then you can study various aspects of the Kondo phenomena. And more generally, of course, the general ideas on effects of strong correlation on metallic systems have a nice playground, as we're going to continue to see in the Kondo lattice model. All right, so the language we're going to use today is the language of pseudo particles or partons or spin-ons, where you take your spin operator and write it in terms of some what we're now calling F fermions, which have a spin, which obey a constraint. There's always only exactly one fermion on each side to make sure that there's only two physical states, spin up and spin down, on the right sides. So this immediately, this is an operator that must be obeyed at all times. So it commutes with the Hamiltonian. And in some sense, because it's true on every side, you have an infinite number of conservation laws. And so that plays an important role in generating what's sometimes called an emergent gauge field. And that's kind of what we're going to see today. Finally, the gauge field come alive as the real excitation. So far in the mean field descriptions we've been following, it's just kind of a side observation, but doesn't play much of a role. And we'll also see why it doesn't play much of a role in some phases, but plays more of a role in other phases. Okay, but this is the underlying gauge symmetry associated with this conservation law, and the Hamiltonian, which I haven't written down, but wrote pictorially. The only places the F appears in the Hamiltonian are in this combination. And this combination is explicitly invariant under this transformation where chi can be an arbitrary function of space. Now, when you do time-dependent phenomena and use the path-integral language, then chi can also become independent of time, dependent on time, but that's not a complication we're going to pay much attention to, at least in our first treatment. All right, so what we do is we just take this in the mean field treatment, which becomes exact as the number of spin components alpha becomes large. In the mean field treatment, all you do is just you insert this operator in the Hamiltonian and do the only trick we know so far really in dealing with many body systems. You factorize. You just factorize the full fermion term into products of two fermion terms. And the constraint you just impose by introducing a Lagrange multiplier or chemical potential, which we call lambda, and just adjust the value of lambda so the constraint is satisfied. Okay, so that's what you do. And when the dust settles, you get a set Hamiltonian, which is here. A set of constraints that have to be satisfied by the parameters in the mean field Hamiltonian. The parameters we don't know are QBar and lambda bar, and these have to be chosen so that these equations are satisfied by the usual tricks of Hartree-Fock. There's this parameter n floating around for our discussion. N is just 2. Anywhere there's an n, you replace it by a 2 for our discussion. I'm doing, of course, in the notes, I've done it more generally, in case you're interested someday to compute the corrections to the mean field theory. But we are only going to talk about mean field generally today. Okay, so now we just faced with solving these equations 2, 3, and 4. We have to solve for Q bar and lambda bar. At 0 temperature, that's what we're going to do now. Okay, so that's now it's just kind of a mathematical problem or a technical problem where you have to figure this out. So the simplest way to do this here is to just compute the Green's functions. And so let me write down some Green's functions of this. So here's the Hamiltonian. There's two ways to proceed. You can just rediagonalize the Hamiltonian, as I showed you last time. If you take the Hamiltonian, it had these eigenvalues and some eigenvectors. You can define new operators that create the eigenvectors and then work in terms of the new operators. That's effectively what we did for superconductivity. We had the new operators, which is the Bogoliubov operators, and then you wrote everything in terms of the Bogoliubov operators. You could do exactly that here. The only difference is you're mixing C and F rather than mixing C and C dagger. Okay, but that's all. That just changes a few signs here and there, but everything's the same. But I'm not going to do that. I'm just going to actually just use pictures because it's, in this case, that's even easier. You could do that, but you don't have to. So the way I'm going to think about this is I'm going to treat the Q bar just like we did the impurity problem, although here it's not necessary because you can diagonalize the whole thing. It's diagonal in K. I'm going just to treat the Q bar as an interaction. So my Baire-Green's function will be purely diagonal. Will be I omega. So I'll have a Baire-Green's function. And so this is what you do. You have a Baire-Green's function, say J0 of C of K and omega n. V1 over I omega n minus EK. And G0 of F will be dispersionless, but I'll imagine it also depends on K. Minus lambda bar. And graphically, I'll represent this by a line, which let's make this a full line, and let's make this a dashed line. So my only interaction is I can represent by an X. It converts a full line to a dashed line, and that picks up a factor of Q bar. Okay, so now I want the full Green's function. I want everything, not just the zeroth order. So GC, well, diagrammatically, that's going to be one full line plus, Q dashed line, and then another Q, and so on. There's an infinite series. So from this, you can see if I define the self-energy for C particles with respect to cutting only a C line, I think of the F line as some interaction. So the self-energy would be I'm allowed to cut the C line. So then in this case, what you see is that I can cut a C line here, internal C line, and it falls apart. So this term really should be part of the should be included in the self-energy. And in fact, you can quickly see the self-energy is very simple. The self-energy sigma C is just equal to this. That's it. And there's no other graph. That's the exact answer. And if you put this in Dyson's equation, then you get your GC. So that tells me what GC is equal to then. So GC becomes the original Green's function, I omega n minus EK, minus the self-energy. And what's the self-energy? Well, there's a factor of Q from here and here. So it becomes mod Q squared. And then there's a propagator of the F. That becomes I omega n minus lambda bar. Okay, so that's the answer that's written down here. That's this. And then you can buy exactly the same trick because the graphs here are all simple. It's just all the graphs are just these lines. And every line carries the same momentum and frequency. So it's even simpler than the Kondo impurity problem because every line has the same K, and omega. So there's no summation even. It's just a product. So you can quickly work out that these are correct. Okay, so these are the three Green's functions. So now that I have the Green's functions, I can just plug them in here and finally get my two equations. So I do that, and that's how I get them. This is the equation for QBar. We'll simplify this a little bit and then tell you the equation for lambda bar. So this is one of the equations. There's an overall factor of QBar, but just like for the Kondo problem, we won't cancel it out right away, just in case QBar equals 0 is the only solution. So we'll keep that. And then we have to do the summation over epsilon and K. So omega and K, that simply comes from the summation of, here we go. There's a summation of K over here that just comes from the mean field equations. And you have to do the, since this is an equal time correlation function, you have to sum over the frequency. Okay. So when you do that, well, this looks exactly like a Linhart function because you can quickly see that this is in fact nothing but, can be rewritten, the denominator is nothing but I omega n minus EK plus times I omega n minus EK minus. EK plus and EK minus were the eigenvalues of that Hamiltonian. You know, here's EK plus and EK minus. So this looks like, again, just like a Linhart function, but with two different bands. So the Linhart function was at the same band, same EK on both. This has different EKs, but the frequency summation doesn't care. You just do it usually, and you get exactly the Linhart type susceptibility, but except the Fermi functions have different energies corresponding to different bands. They're all at zero, it's the same momentum. All right, so that's the QBar equation. And now you have to evaluate the Fermi function. And this is where this picture from last time comes in. You know, so we had this picture that to begin with, lambda bar, the F band was half occupied. So it had exactly half an electron in it, one electron in it, because it could take two. And the C band has rho C electrons in it. And there's a connection between, you know, KF and rho C. That's just the Lattice here. If this is 1D, that's easy to write out. I'm just drawing 1D pictures. So in 1D, rho c, the total number of electrons, is basically the integral 2 for a factor of spin. Let's say the momentum is around 0 minus kf to kf, dk over 2 pi. And that gives me 2 kf over pi. So there's a very direct relation between the Fermi wave vector and the density. So we assume that the density, so now I should, since I'm going from minus pi to pi, then this should be 0. I assume there's a mirror image on the left-hand side, which I'm not drawing. Okay. So this is the band, and it goes the other way on the side. So this kf here is just determined by the conduction electron. But once they hybridize, what happens is that the half-filled lambda band, all the electrons, you don't care, they're mixed up, want to occupy the lowest band. And what I assumed was that they would occupy this hybridized band, this lower purple band, and the total number of electrons in that is 1 plus rho c. So that means the new kf has to accommodate, since there's only one band, has to move up. So the kf becomes large. And that's the origin of the word large Fermi surface. So here, what's happening is something quite remarkable, that you have these stationary electrons. They're not moving at all. There's no term in the Hamiltonian that actually moves the charge of this electron. This is our Hamiltonian. It's a pure spin. It could even be a nuclear spin. It's just a qubit. It's a two-level system, this thing. It could be some other two-level system. It could be a superconducting qubit. It could be a Rydberg atom. It could be anything. It's just a two-level, degenerate two-level system with this sort of interaction. And nevertheless, this two-level system kind of has become a fermion. It's become an electron and hybridized with the moving electrons to form a bigger Fermi surface. And so when you think about it that way, you see this is really quite an amazing thing. And in fact, it's observed, it is what happens, that two-level systems can hybridize. Where did that picture go? Can hybridize with moving electrons and effectively become fermions. So you should really almost even think of these this large Fermi surface as built up of some emergent fermions that weren't there to begin with because there was nothing that was allowed to move. But now they're there because the Fermi surface has become large. Okay. All right, so now where was I? So now what we have in this picture is that only the lower purple band is occupied, but the upper band is totally empty. So if that's the situation, I mean, it may be slightly different depending on the complicated band structures, but that's the simplest situation. Then this f of ek plus is just 0, so we can throw that out. And at 0 temperature, and you only have this term here, and ek plus minus ek minus is a simple expression which you can evaluate. And so finally, we get our expression for the equation for QBar. Here's our expression. It's somewhat different from the Kondo impurity expression. There's no Lorentzian here that you have to integrate over, but there it is. Okay, it's little more complicated. So now we can stare at this equation and ask, is QBar non-zero? Because once QBar is non-zero, we're having this rather amazing phenomenon. We're having this phenomenon that the qubit becomes a fermion. Okay. That's what we're led to by this mean field theory. There's no other choice. So is that what has to happen? So one way you might think maybe this won't happen is if JK becomes very small. So if you make JK smaller and smaller and smaller, maybe this qubit will just remain a innocent qubit. It won't just become a fermion by melting into the Fermi sea. So we ask, as you make JK go very small, is there a non-zero solution to this? Other than, of course, QBar equals 0. So as JK becomes very small, the left-hand side becomes very large times QBar. So there's a very large coefficient of QBar. So the only way we'll have a solution of this is if this object also becomes very large as JK goes to 0. Now, the only thing we have at our disposal is QBar. So if you want to make the left-hand side really large, you want to make QBar very small. So let's ask what happens as QBar goes to 0. So at QBar goes to 0, this thing, you can now convert the summation over K to an integral over the density of states. This basically becomes, as QBar goes to 0, an integral of the density of states from some negative energy, some bandwidth, let's call it D, to 0 of this energy, and that energy is just the modulus of the energy from the Fermi level times D of E. Okay, lambda bar is, well, we have to figure out what lambda bar is, but this could possibly, this EK minus lambda bar could be going through the Fermi level. So now what happens as Q bar goes to 0, as we'll see, lambda bar also goes to 0. So I'm assuming that, okay, sorry. So we just assume that as Q bar goes to 0, lambda bar also goes to 0, and I'll show you that in a minute. Anyway, so then what you see, this thing is log divergent. So the Kondo log survives in this, at least in this mean field theory. And so since this survives, it means that there's always possible to get a non-zero Q bar solution other than Q bar equals 0. And that will also be the lower energy solution, and that's something you're going to look at in the I think, a homework problem that I have in mind. All right, any questions? Okay, then moving along, there's the other equation we have to solve. Where did it go? This equation. So you just evaluate it a little more and with the same tricks, and it's a little more complicated looking equation that you get. Okay, and finally, we also need to keep track of the Fermi wave vector and what the, to fully understand the structure of equations 11 and 12. And that I've already kind of assumed. That's what I did with these pictures. There's a constraint on the values of KF, depending on whether, when Q bar is non-zero, 1 plus rho C must equal this area under this KF. And the other statement important to make is that this constraint is actually exact. It's only true to main field theory. It's true to all orders and computations by the same kind of analysis we did for the Lattice theorem. So, but if you don't, so we just forget about the general analysis. This is the statement that I had illustrated in pictures, that the region of K space where the EK is less than 0 must add up to a density of rho C plus a half per spin. Rho C is the density of conduction electron per spin component. Okay, so that's correct. All right, so now this gives you the value of KF and the range of integration. So there's a bit of algebra there. I think I'm just going to skip the algebra because it's a little tedious, but it's doable. And I will just tell you the answer. So in the limit of small Q bar, you can solve for lambda bar and Q bar. And these are the answers you get. They're right here and here. So lambda bar turns out to be of order Q bar squared, where D of 0 is the density of states at the Fermi level. And Q bar, lo and behold, it's almost exactly the same expression as for the Kondo temperature of the lattice model. I think there's a factor of 1/2 here, which is different, that we didn't have for the Kondo model. So there's actually two differences from the Kondo model. In the Kondo impurity model, lambda bar is exactly 0. Here it's not exactly 0, because you can just see from this band structure here, this picture, there's no symmetry between particles and holes. The occupied side looks very different from the unoccupied side because the bands have all mixed up. So lambda bar is not exactly 0. It's not, so the F band is close to, but not exactly at the Fermi level, the pair F band. but it mixes up with the C band anyway. Anyway, so Q bar as JK goes to 0 is exponentially small, and it's an expression very similar but not identical to the Kondo temperature. Okay, so all of this work was to establish two important things. One is that the Fermi surface is large, meaning the qubits have become fermions. And two, that there are now mobile quasi-particles at the Fermi level, but they're very heavy. So how do we see that? Well, in other words, which I showed you in pictures, let's now see that analytically and actually get some numbers. I showed you in pictures that the band is really flat here. So that means the particle is moving very slowly. The velocity is very small. At the Fermi level, the Fermi velocity is very small, which means that the particle is very heavy. How heavy is it? Well, we just look at our Green's function of the conduction of electrons, which is what you'd measure in a photo emission experiment. Here's the Green's function. Okay, so we know lambda bar and we know Q bar. So this is quite easy to work out what this is going to be. So the Green's function I can write as G inverse is equal to, hello? Yeah. Okay, you have to actually, did I do that right in the notes? What did I do? Yeah, so here I mean, this is, yeah, let me just do what I did here. It's not exactly right. I'll have to correct it because the actual dispersion is capital EK, not small EK. And I should really play with that. But let me just ignore that small difference because it, but anyway. So, yeah, sorry about that, but I won't be able to get that right on the spur of the moment. So G inverse is I omega n minus EK. And then I assumed in the notes that I can just throw out this omega n. So let me just imagine that's correct. It's not exactly correct because the pole is slightly shifted. You know, so then I get I omega n plus Q squared over lambda bar. Sorry. Oh, and then you keep one more order, and then you make plus I omega n over Q squared of, what did I do? Yeah, you assume that lambda bar is large, so you keep that. Then you expand it out, so you'll get lambda bar squared. Is that right? Okay, sorry, I should have checked that. You know, I prepared these notes a couple of days ago, and that's my lifetime of my brain these days. So what do you get then? What's going on? Not quite. Okay, am I doing that expansion right? Sorry. Yeah, no, I didn't do that right. I've even forgotten how to do a Taylor series. Okay, so I write that as, let's do it carefully. So I'm just going to take that as mod Q squared times, I pull out a lambda bar minus lambda bar times 1 minus I omega n over lambda bar to the inverse. Okay, so far no approximations. And now I expand that out. I get rid of the inverse and I put that a plus. Okay, that's an expansion. And okay. And that's back to, if I did it right, let's see. Lambda bar. Yeah, okay, that's correct. All right. So that I can rewrite as I omega n. And then I multiply by a factor of z. Well, okay. Okay, so this thing is approximately, so it's approximately equal to this. And I'm going to now claim that this is basically z over I omega n minus ek over z ek tilde, where I'm going to approximate pull the coefficient and make it constant here. All right, so you play that, and here's what you get. Okay, that's just trivial algebra. So when you just expand that out for small I omega n, you get this expression here. Okay, which should have been a times z. You pull out a factor of z, and z was q bar squared over lambda bar squared, but lambda bar is this, and so if you put that factor value of lambda bar in, this is what you get. Okay. All right, so that was a needlessly complicated way to just simplify that. And okay, so the important point here is that this factor z. So the z is very small, goes as q squared, which is then the Kondo temperature of the Kondo temperature, and it's much smaller than 1. Okay, so what are the consequences of the z being much smaller than 1? One is that the quasi-particle residue. So if you did some photo emission experiment and you're looking for the peak in the quasi-particle pole by some sharp scattering onset near the Fermi level, the strength of the peak will be very small. So, or in other words, the overlap between the bare particle, the bare electron, and the renormalized quasi-particle is very small. It's not 0, but it's small. Secondly, there's a factor of z here, which is much smaller than 1. And that means the effective mass, m star, is roughly the bare band mass divided by z. So as z goes to 0, m star goes to infinity. And that's the basic heavy fermion. So we found our heavy fermion. And what we have seen is that the renormalization of the heavy fermion, what makes the band so large, mass so large, is its exponential factor, which can, be 1,000 quite easily in a typical material. And so consequently, the effective mass of the electron can be very heavy. And in some sense, it's really heavy because most of the electron is actually a qubit. Only a little bit of it is moving around. That's why the quasi-particle residue is so small. The qubits are basically stationary, but roughly speaking, some part of them have become a fermion. And that part moves around. On the other hand, for the Fermi level, for the Fermi wave vector, that's the amazing thing about the Lattice theorem. It doesn't matter that z is really tiny. It doesn't matter that the overlap of the actual fermion with the bare electron is very tiny. You still count it as one state when you're counting the states inside the Fermi surface. So the states inside the Fermi surface, in some sense, count the renormalized particles, not the bare particles. That's the content of Lattice theorem. All right, so that's really all I'm going to say about the Kondo lattice problem. There's actually quite an extensive treatment of this and the Kondo lattice physics, if you want to learn more, in this book by Coleman, which is also listed on as one of the subsidiary books of the course. There's at least a couple of 2 or 3 chapters towards the end where he discusses everything I've said and more on the Kondo problem. Yeah, but okay, I think my treatment is a bit more compact and gets to the basic physics also. All right, any questions on the Kondo problem in general?
I was wondering when rho c is equal to 1/2. Do we have an insulator?
Correct. Yes.
Oh,
So if this
okay.
band is exactly filled, yeah, so you can see this from this picture. I mean, it depends, but you can. You need not, but it depends. So if your KF is exactly pi here, and this band, what happened here? If your KF is exactly pi, then the purple band will be completely filled, and that's what's called a Kondo insulator, where this gap between the occupied band and the unoccupied band is very small. It'll be of order the QBar. So Condo Insulator is a compound where the rho c is exactly 1/2 or 1. I'm sorry, I think in my pictures, rho c was number of electrons per site in the conduction band. In my notes, it's number of electrons per site per spin. So sorry about that inconsistency. When in doubt, just go with the notes. So
and also,
yeah.
I was wondering, like, if we increase it like larger than 1/2, then we get Fermi liquid again. But in this case, we have like usual Fermi liquid because it's, I mean, Fermi surface is
It
small.
depends. If you go larger than 1/2, there's a window here where your Fermi energy is here. Then it's still a heavy fermion.
Oh, okay.
So,
But with small
when
Fermi
you get
surface.
up here, yes, then it becomes an ordinary Fermi liquid. But at that point, roughly speaking, the F band is way below the Fermi level, and it makes no difference. Yeah, you'd have to give up. Okay. What I was saying about Condo insulators, the band gap is very small and it's highly renormalized from what you might expect. So formally a Condo insulator is smoothly connected to band insulator, but it's highly renormalized by the Kondo effect. In the same way that a heavy Fermi surface is smoothly connected to free electrons, but qualitatively it's very different, quantitatively, excuse me. And also it could be that you don't get a Kondo insulators, and that's, this picture is too simple. This picture is only in one direction in K space. There are multiple directions in K space, and it could be along some directions the lower band is always below the upper band, but in other directions it is not. And so life in the real world can be quite complicated because of the multiple dimensions in K space. And and there are a few examples of Kondo insulators now. I think samarium hexaboride is one of the very few ones, and people are studying that a lot these days, because in addition to being a Kondo insulators, it also has large spin orbit coupling and possibly what you call topological band, but that's a topology of a different type. That's topological band structure of the Kane-Millet type, where you get edge states because of band inversion. But that's still it's essentially a free electron problem. That's discussed also in Coleman's book.
Yeah, okay, thank you.
But what is not discussed in Coleman's book is what I want to discuss now, is a topological phase in the sense of bulk topological phase. Nothing to do with edge states. It's really a topological phase in the sense it has an emergent gauge field. So that's has anyons, and it's a whole. It's kind of like the difference between the fractional quantum Hall effect and the integer quantum Hall effect. The edge states that Coleman discusses for samarium hexaboride, like the integer quantum Hall effect, is simply free electrons. But now we're going to talk about a more exotic type of topological order, which only in the last 2 or 3 years, there's been now, I think, fairly good evidence that it actually occurs in real life. So then I don't feel embarrassed to talk about it, because this was a kind of phase that we call it the fractional Fermi liquid that was proposed by Senthil, Voita, and myself. But let me just at least give you the basic idea and introduce what is an emergent gauge field and how that's another natural fate for the Kondo problem. Okay, so what we're going to do now, yes.
So one was, is there some qualitative difference when you have some coupling between the sort of stationary spins as well, like the Heisenberg interaction that we kind of neglected?
That is exactly the point I'm going to now discuss.
Oh. Okay.
Good. But I would say, in the real world, there's always a Heisenberg coupling. That is exactly what I was going to say. So there is a coupling here between the Kondo spins here, this J sub h, which is always there. I mean, it may be very small. And what that J sub h does to the heavy Fermi liquid phase, is not clear. I mean, it's very hard to, in fact, tell. So in the treatment so far, I've just assumed it's small and just put it equal to 0. So now I'm going to do another treatment where I'm going to do, again, a mean field theory. So in mean field theory, we want to find at least, can this J sub h leads to a different type of a phase? And the answer is yes. And I'll describe what that phase is. But that's still a long way from answering whether an actual system with a given value of JH is going to do that, because mean field theory may not be a good guide. So that's something to keep in mind. I'm just going to do mean field theory, but that doesn't immediately mean we can believe it, because it's a question of numbers, as we'll see, whether this more exotic phase appears or not. So in a nutshell, what happens in the more exotic phase is that the qubits remain qubits. They remain like spins, but they form singlets not with the conduction electrons, but with each other. And the conduction electrons move as they were before. It's as if the qubits were not even there at the level of mean field theory. So the Kondo effect has completely disappeared. And the conduction electrons, the mobile electrons, is now just densities rho c. It's not 1 plus rho c. And so the Fermi surface becomes small. Okay. So, from one point of view, that's, that's obvious that should happen. On the other hand, we had this Lattice theorem that really dominated condensed matter physics for decades. And from the point of view of the Lattice theorem, it's not at all clear that such a thing is allowed to happen. So you have to show exactly why the Lattice theorem fails. And to show that, the idea of emergent gauge fields is absolutely crucial. So this can only happen. So one of the things we proved in our paper was that you can violate the Lattice theorem if and only if there is actually an emergent gauge field. There's a real excitation, which is a gauge field that's sitting on the qubits. Okay, so that's kind of what I'm just going to sketch the argument now and leave it at that.
I see, thanks. And a second question I had was, so you mentioned that for the Kondo impurity model, you can get that if you have one type of metal and you dope it with some other kind of metal impurity. For the Kondo lattice model, what kind of systems behave like that? Is it actually like two different species, or is it some inner electrons and outer electrons? Or
it's invariably two different species. Well, at least in this application we know so far. In principle, it's possible that it could be different orbitals in the same atom. But all the well-known cases, something like, let's say, cerium, cobalt, indium-5, which has been studied a lot, and uranium, beryllium-13, uranium, platinum-13. The qubits are on the uranium, and the conduction electrons are mostly the platinum, and so on. So it's different. They're different. They're called intrametallic compounds. They have two different metallic ions, and one of them has electrons that don't like to move but have a free spin, that they're not paired up.
I see.
So that's the typical situation, and there's literally hundreds of compounds like that. Okay. In some of recent work in our group, we've been actually even exploring the idea that even in the cuprates, where there is only one kind of atom, the copper atom, there still could be some kind of Kondo physics happening, but that's a more complicated speculative idea. at this point. But yeah, so let's, okay. All right, so now let's do a mean field theory on this model with the J sub H term. Okay. So that's the Hamiltonian here. It's called the Kondo Heisenberg Hamiltonian. So that's the Kondo lattice model plus an interaction J between the spins, which are now, I've dropped the D index here. I'll probably put it back in. And what are we going to do with the spins? Well, we're going to turn the same crank. We're going to write the spins in terms of the F fermions. No change really. We already know how to treat the S dot S interaction. We just factorize it. And so now we go ahead and factorize. And what do you get? So when you factorized the Kondo interaction, you got the Q field. And so now you're going to get another parameter, which I'm going to call the P parameter. Okay. But there's a very important difference between the Q field and the P field. And that plays a crucial role in deciding what the ultimate fate is under this gauge symmetry. So we may as well draw another picture here. So we have the conduction electrons. And these are moving around. That's the C alpha. And we're going to couple them to the spins on this line now. And now there's F. I just want to draw an arrow to just keep in mind that the F's don't move on their own. And on each such link, I had a Q, which was of expectation value of C dagger F. But now let me put a site index. This is the same site I, but there's two bands. So CIFI. So now on this link, I'm going to get a P, which is going to be F dagger I, FJ. Right now this side is I and that side is J. And so P, so here Q dependent on the site, but here P depends on the links or the bonds of the lattice. And this has a huge difference on the gauge transformation. So remember the gauge symmetry was Fi going to Fi e to the I chi I. So if I just look at this, and C is a gauge invariant physical fermion, it's not a qubit, then P Qi went as Qi times e to the I chi I, and the Pij will go as Pij times e to the I chi I minus chi j. The minus because there's a dagger here. Okay, so you can see that the gauge transformation of the Q's are completely different from gauge transformation of the P's. All right, so now we're going to take some kind of low energy continuum theory. We're going to try to figure out what's happening at low energies. Now that's actually a very complicated business because exactly how you take these gauge dependent variables to low energy can become very complicated. I'm just going to make the very simplest assumption here. I mean, that's really the heart of studying spin liquids in emergent gauge field is to get that continuum limit right. And you get different phases, different types of topological order, depending on exactly how you do it. But we just take the most simplest assumption here, that in the continuum, so then Qi goes to some slowly varying field, which will be Q of R. And everything will be a smooth function of R. then what will Pij goes from? Well, let's take the I in the x direction, let's say in the plus x hat. Well, that will go to some P sub x of R in the x direction. So that's the continuum. And what's the gauge transformation? Well, then P sub x of, so Q of R will transform just like this, e to the I chi of R, which is continuum. But what about P of R? Well, P of R, Px of R, we'll write as a modulus of P, which will in fact be R independent. That's not the important point. The important thing is the phase difference here. So we're going to, and I'm going to go ahead and call the coefficient here A sub x of R. And now you can see that in the continuum, A sub x of R goes to, under gauge transformation, A sub x of R minus grad x of chi. Because this difference becomes a gradient. Lattice spacing is equal to 1. All right, so this tells me that the phase of Pij is an emergent gauge field. Okay, so the moment you have this Pij variable, even for the Kondo lattice heavy Fermi liquid phase, you do have this in principle, and I'll discuss in a minute why it's not so important there. So the phase of Pij is an emergent gauge field. And what does this mean? Well, so let me say, now I'm going to just use the gauge symmetry to write down some low energy theory in the spirit of Landau-Ginzburg theory for the fluctuations, corrections to the mean field theory. So the low energy theory, the effective action of the Lagrangian S effective of, let's see, of Q and phi. So I have two continuum variables, Q of R and A of R. I have a vector field A. I also can do that in the Y direction also, and I have the Q. So what does the effective Lagrangian look like? Well, it's going to, the only thing it can have with respect to A is the Maxwell term. That's the only thing that's gauge invariant, at least in the continuum. So it'll be dx ay minus dy ax squared. So that's the Maxwell term with some coefficients, okay, there. Then what about the Q's? Well, with the Q's, you could have a term like this. You could have K tilde of gradient of Q, but it has to be gauge invariant. So the only way it becomes gauge invariant, it has to be gradient minus IA of Q mod squared. And then you could imagine some polynomials, R Q squared plus U Q to the fourth. Okay, so I'm just being very sketchy without even doing any work. I'm just trying to figure out what does the gauge invariance tell me on the low energy theories. Well, the gauge invariance tells me that there's this Q field that can fluctuate. It can, and then there's a gauge field that can fluctuate, and I ignore everything else. And I just write down the minimal, simplest term that can couple them together, consistent with the gauge symmetry.
So here, may I ask?
Yes, Juven.
Here the gauge group structures U1, and what's the criteria or constraint that what kind of a gauge structure may be possible? Can be.
Yeah. So I'm keeping the, of course, yeah. Like I said, they can be all kinds of. The gauge group is U1, but it could be broken in all kinds of different ways. You could even have a SU2 gauge group depending for a different factorization of the spin dot spin term, as you know. So there can be many complicated things. I'm just trying to right now to someone who's never seen emergent gauge field before, just make a couple of basic points. So we'll return to it. I have 2 minutes left, so let me just make the main point, and then we'll come back and discuss it more. So the main point is the following. So there's two possible phases in this simple mean field theory. Phase A is r less than 0. Then if I look at the potential for Q, this is as a function of Q, the energy will be at some Q bar not equal to 0. So this is the phase that we've already met. So what happens here is Q condenses. And the gauge language, you call it the Higgs phase, because you have a charge 1 boson that's condensed, Higgs phase. Because if you just look at this action, this is exactly the action for a boson, which has charge 1. Okay, under this gauge field. And that's pretty much required by this, by this gauge transformation. This goes like this, and this goes like this. Well, that's the only way you can get a gradient that's gauge invariant. Okay. Now, what does this mean? Once Q bar is condensed, well, then you can write Q as Q bar times e to the I theta of r. You just look at the phase fluctuations of theta. And when you do that here and you plug this in here, then what is the action for the gauge field? And then L of A has a term which is K tilde. If you just put this expression in here into this gradient term, it becomes A minus grad theta whole squared times Q bar squared. Something like that. And now you can choose a gauge, and I'm Rashik here. We'll come back to this in much detail next time. I can choose the gauge and just get rid of this actually, just by a gauge transformation. So what this becomes then, this is the Higgs mechanism. This is what one of the things that Higgs got the Nobel Prize for. It's not the Higgs boson, but the Higgs mechanism. So you get a term here, which is A squared, which means the gauge field has a mass. Okay, so you found this emergent gauge field. This is not the electromagnetic gauge field. This is nothing to do really ultimately with electromagnetism or superconductivity. It's some internal emergent gauge field representing the couplings between these qubits. And this emergent gauge field has become massive because it's got an A squared term. So once it's become massive, this Maxwell term doesn't play much of a role. And in fact, this is why the theory of the heavy Fermi liquid that I presented today is fine. I didn't say anything about gauge fields. In fact, Coleman never mentions gauge fields. But there's a very successful theory there. And why is a successful theory successful? Because if you try to really think more deeply about gauge fields, you end up with the conclusion that in the phase where Q bar is equal to 0, the gauge field is massive. And so there is no extra long range effects that we've forgotten which destroy the Fermi liquid behavior or anything. The Fermi liquid behavior is correct. However, and I'll just stop with there. There's another phase, B, where R is greater than 0 in the potential. So the potential as a function of Q now here. And now the minimum is, the only solution is Q bar equals 0. So far, I've said there's no such solution, but we'll find now once you put in the P term that there is such a solution as LR. And now, once Q bar is 0, then the gauge field comes alive. And the gauge field is actually there. And in principle, you can measure it in experiments. And that's a whole new phase of matter, which we call FL star. Okay. So I'll say a bit more about that next time, and that will be the end of Kondo physics. Also, I should say that it turns out that I was lucky enough to get a vaccine appointment like just before class on Friday. So I'll send another notice on this once I figure it out in detail on Slack. But it could be that class on Friday will start a bit late, like 15 minutes late or something. And if they really screw up my vaccine, then I may have to cancel it. But I've sent a notice on that. But I think I should be able to come back here after getting my vaccine and start pretty close to time. Let's say 15 minutes to be safe. Okay, any questions? All right, great. So yeah, go ahead, Anand.
I was just saying, congrats on the vaccine.
Yeah, I know. I finally became eligible this week. So
Sophia, it's also possible you can bring the computer to the hospital. So you can also do so.
I'm going to the CVS, which is nearby, and my appointment's at 11:30. So they said it should be on time. So I should be back here. It's just right down the street. We'll see. Well, I'll send an update from there, and what time I'll be. I think class will start, or I may just cancel it. Let's see. But I think I'll be here.
Be safe. Thank you.
Okay. All right. So, and there will be a discussion session tonight at 9 p.m. Okay.